So we know that the protons and neutrons are held together by the nucleus by the strong forces. One way that scientists love to study some things is to tear said things apart. If we want to learn more about the strong force that holds nucleons together, we can examine how tightly bound the nuclei are by tearing them apart. The energy required to disassemble the nucleus of an atom into separate protons and neutrons is known as the binding energy. Now, since it requires energy to tear the particles apart, it implies that the energy of the two separate nucleons is more than the energy of the two nucleons that are bound together. And if we take Einstein's energy equation where energy is mass, then that must mean that their mass of two protons, separate, must be more than the mass of both of them bonded together. We can look at this graph at the binding energy per nucleon. We see some interesting things. This graph is showing us the amount of energy that it takes to bind a certain number of nucleons together. We can see there's a really low energy for hydrogen and helium, a bit more for lithium and boron. This means that these atoms have a low binding energy and have the least bound combination of nucleons. Then we find that there's a peak right around 8.8 megaelectron volts. This peak coincides with the mass number for iron, and it tells us that the iron is the most stable configuration because it has less energy per nucleon than other elements. If we take hydrogen 2, for example, we have one proton and one neutron, and they have a certain amount of strong force that must hold them together. Helium-4, on the other hand, has two neutrons and two protons that can arrange themselves in a more three-dimensional configuration where they all attract each other. The nucleons are able to arrange themselves so that they are closer together, and as a result, it takes less energy to hold them together. So for low-mass nuclei, each added nucleon forms bonds with all the other nucleons in the vicinity. This continues up until the mass number becomes about 60, or roughly the mass number of iron. At this point, the nucleons are too far apart to feel the other attractions, and if one of those nucleons is a proton, there starts the beginning of some proton-to-proton repulsion. Ultimately, what happens is as we add more protons, the electrostatic repulsion becomes more and the nuclei become less and less stable. And really, once you get over past uranium, where we have a binding energy of only about 7.5 megaelectron volts, we don't find any stable elements past that. In 1939, it was discovered that a uranium nucleus could split in half when bombarded with a neutron. When the neutron combines with the nucleus increases in energy, causing it to destabilize. The nucleus breaks into two roughly equal parts along with a few neutrons. For example, a neutron is smashed into uranium-238 to form uranium-239. This intermediate nucleus is called the compound nucleus and typically is so unstable that it only exists for a very tiny amount of time. And by tiny amount of time, we are talking along the lines of 10 to the negative 12th seconds. Once the neutron is added, the intermediate atom fissions to become xenon-140, strontium-95, and 3 free electrons. This liquid drop model was developed to help explain this type of fission reaction. Basically, it says that when the nucleus is bombarded with a neutron, the nucleus absorbs the neutron's mass and the energy associated with that neutron. This collision increases the energy of all the other nucleons in the nucleus, causing it to elongate. This change in distance between the nucleons causes the strong nuclear forces between the nucleons to decrease. The decrease in the strong nuclear attractive forces causes the repulsive electrostatic forces of the protons to overpower the strong forces. As a result, the nucleus splits apart, or fissions. We want to examine the energy change for this type of reaction because it is not really what we would expect. We started with uranium-238, which has a mass of 238.050784 atomic mass units. We end up with xenon-140, strontium-95, and 3 free neutrons. All these in total have a mass of only 237.866993 atomic mass units. What we find is that in nuclear fission, just like it is in this example, the mass of the products is considerably less than the mass of the reactants. Now, if there's a decrease in mass in a reaction, there must be a decrease in the total energy as well. That must mean that energy is released during a fission reaction. We know that the energy released is equal to the mass that is destroyed, which is just the difference between the total mass of the products subtracted from the mass of the original uranium. In this case, the change in mass is 0.183791 unified atomic mass units. Using our E equals mc squared, we can find that 171.2 mega electron volts of energy is produced. Now, something to keep in mind is that fission does not always produce the same products. Most fission reactions, however, do produce free neutrons. And this aspect is pretty important because these neutrons can then go on to induce more fission reactions. The neutrons produced in a single fission reaction can go on to collide with other unstable atoms in a sample. This can lead to other fission reactions. If this continues to happen, then a chain reaction is induced and fission just keeps going on. This depends on several things, such as the number of neutrons produced and the amount of unstable nuclei nearby. It is also important to note that not all neutrons will induce a fission reaction. Some neutrons will escape the environment, while some will be absorbed by the nucleus that does not undergo fission. Mostly this depends on the amount of available material. The minimum amount of material that is required to create a self-sustained chain reaction is called the critical mass.